In this video, we're going to explore some of the most important cloud computing concepts that every developer, engineer, or tech enthusiast should understand. If you're new to cloud computing, this will give you a strong foundation. And if you already have some experience, this will help reinforce key ideas and connect them together more clearly. We'll go step by step, building from simple concepts to more advanced ones. So by the end, you'll have a much better understanding of how modern cloud systems actually work behind the scenes. Let's dive in. Let's start with one of the most fundamental ideas in cloud computing: scaling. Scaling is all about how your application handles growth specifically, how it responds when more users start using it. Imagine you build an app. At first, only a few people use it, so everything works perfectly. But then suddenly, your app gets featured on social media or a news site, and thousands or even millions of users start accessing it at the same time. Without proper scaling, your app might slow down, return errors, or even crash completely. This is a very common problem, and solving it is one of the main reasons cloud computing exists in the first place. There are two primary ways to scale an application. The first is called vertical scaling. Vertical scaling means improving a single machine by adding more resources, like increasing its CPU power, adding more memory, or expanding storage. Think of it like upgrading your personal computer. If it's slow, you might add more RAM or get a faster processor. This approach is simple and straightforward, which is why it was commonly used before cloud computing became popular. However, it has limitations. First, it becomes very expensive as you keep upgrading. More powerful hardware doesn't scale linearly in price. It often gets disproportionately more expensive. Second, there's a hard limit. At some point, you simply can't upgrade the machine any further. And finally, there's a major reliability issue. If that one machine fails, your entire application goes down. So while vertical scaling works for smaller systems, it's not ideal for large-scale, high-traffic applications. This brings us to the second approach: horizontal scaling. Instead of upgrading a single machine, horizontal scaling involves adding more machines and distributing the workload across them. So rather than having one very powerful server, you might have 10 smaller, more affordable servers working together. This approach has several advantages. First, it improves reliability. If one machine fails, the others can continue serving users. Second, it's often more cost-effective because smaller machines are cheaper and easier to scale incrementally. And third, it allows for virtually unlimited growth. You can keep adding more machines as demand increases. This is the foundation of modern cloud architecture. Now, once you have multiple machines, you need a way to distribute traffic between them. This is where load balancing comes in. A load balancer acts as a traffic controller. It sits in front of your servers and decides where each incoming request should go. For example, if a user visits your website, the load balancer receives the request first. It then forwards that request to one of the available servers. There are different strategies for doing this. One simple method is round-robin, where requests are distributed evenly across servers. Another method sends traffic to the server with the least load or the lowest resource usage. Load balancers also monitor the health of your servers. If one server goes down, the load balancer stops sending traffic to it. This ensures your application remains stable and responsive. Next, let's take this a step further with autoscaling. Autoscaling is the process of automatically adjusting the number of servers based on demand. Instead of manually adding servers when traffic increases, the system monitors usage and does it for you. For example, if CPU usage goes above a certain threshold, new servers are automatically added. When demand decreases, those extra servers are removed. This is incredibly powerful because it allows your application to handle sudden spikes in traffic without human intervention. It also helps reduce costs, since you're only using resources when you actually need them. Autoscaling is one of the key features that makes cloud computing so efficient. Now let's talk about serverless computing, which is a major shift in how applications are built and deployed. Traditionally, developers had to manage servers, setting them up, maintaining them, scaling them, and securing them. Serverless removes that responsibility. With serverless, you simply write your code and upload it to the cloud. The cloud provider takes care of everything else: running the code, scaling it, and managing the infrastructure. You don't need to worry about servers at all. Another key benefit is the pricing model. In many serverless systems, you only pay when your code runs. This makes it very cost-efficient, especially for applications with unpredictable or low traffic. However, serverless isn't perfect for every use case, and it's important to understand but overall, it represents a powerful and convenient way to build modern applications. Next is event-driven architecture. In traditional systems, components communicate directly with each other. This creates tight coupling, meaning changes in one component can affect others. Event-driven architecture takes a different approach. Instead of direct communication, components communicate through events. For example, when a user places an order, an event is created. That event is then broadcast to multiple services. A payment service processes the payment. A shipping service prepares the order. A fraud detection system analyzes the transaction. Each service reacts independently. This makes the system more flexible and easier to extend. You can add new features without modifying existing components. This concept is often referred to as publish SRB, where one system publishes events and others subscribe to them. Now let's move on to containers and container orchestration. Containers package your application along with its dependencies, ensuring it runs consistently across different environments. This solves the classic problem of it works on my machine. But when you have many containers running across multiple machines, managing them becomes complex. That's where container orchestration comes in. Orchestration tools automate the deployment, scaling, monitoring, and recovery of containers. They can restart failed containers, distribute traffic, and ensure the system remains healthy. This is essential for running large-scale applications efficiently. Cloud computing also provides different types of storage. Object storage is used for storing files like images, videos, and documents. It's highly scalable and accessible from anywhere. Block storage is more like a traditional hard drive. It's attached to a specific machine and used for things like operating systems or databases. And then we have databases, which store structured or unstructured data. There are relational databases, which use tables and SQL, and NoSQL databases, which offer more flexibility. Choosing the right storage type depends on your application's needs. Next is availability. Availability measures how often your application is operational and accessible. Cloud providers often aim for very high availability, sometimes expressed as 5 nines or 99.999% uptime. To achieve this, applications are distributed across multiple servers and even multiple geographic locations. This ensures that even if part of the system fails, the application continues to function. Closely related is durability. Durability focuses on protecting your data. Cloud providers store multiple copies of your data across different systems and locations. So even if hardware fails or a data center goes offline, your data remains safe. This is especially important for critical data that cannot be lost. Now, let's talk about infrastructure as code. In the past, setting up infrastructure was done manually through web interfaces. This was time-consuming and prone to errors. Infrastructure as code allows you to define your infrastructure using code. This makes it repeatable, version-controlled, and easier to manage. You can deploy the same setup across different environments with consistency. It also allows teams to collaborate more effectively and avoid mistakes. Finally, we have cloud networking. Cloud networks allow you to create isolated environments within a cloud provider. You can control how resources communicate with each other and with the outside world. For example, some resources can be public, while others remain private and secure. You can also define rules that restrict access and improve security. This gives you full control over your application's network architecture. And that brings us to the end of this overview of cloud computing concepts. We covered scaling, load balancing, autoscaling, serverless computing, event-driven architecture, containers, storage, availability, durability, infrastructure as code, and networking. These concepts form the backbone of modern cloud systems. Understanding them will not only help you design better applications, but also give you a strong foundation for learning more advanced cloud technologies. If you found this helpful, don't forget to like and subscribe so won't miss the next one. It really helps to support the content and let me know if you want more videos like this. Thanks for watching, and I'll see you in the next one.